Hello friends, welcome to the mathematical room. I am the caretaker Lucifer. So today we are going to see the second section of the third chapter from Terence Tau's notes, analysis 1. So here we come across something known as Russell's paradox. We have already discussed about it somewhat informally when we studied naive set theory, but now we are going to look at it from the point of view of axioms. So let us see what this thing has to say. It starts like this. So in the previous section we have seen 7 axioms, right? And many of them have a similar flavor. So let's just start this by writing some lines. Many of the axioms in the previous section have a similar flavor. In what sense do they have similar flavor? They allow us to construct sets consisting of objects which satisfy some property, which satisfy a certain property. Okay, for example, you may think of the empty set as the set of all objects which satisfy some impossible property. The set which is the union of two sets, it satisfies the property that it is the set of those objects which belongs to either one set or the other set or both. So just like that, they have this similar flavor. So one might expect that they could be unified if they are coming, if they have a similar flavor, then why have that many axioms? Why not introduce a single axiom which takes care of all of them together? Then it will be much more simple. For instance, by introducing the following axiom. So here comes the 8th axiom. Actually, it will turn out that this axiom is not well suited for our set theory. We will see why. So let's just have a look at the axiom. So this is axiom 8, and like the other axioms, it has a name. It's called axiom of universal specification. We are not writing axiom of since that is understood. Note that we already have an axiom of specification, but this is axiom of universal specification, and there is a warning that goes with this. Tau calls it dangerous, and for good reasons. So let's just see what this axiom has to say. suppose that for any object x we have a property ink. Okay, so for any object x, we have some property pertaining to that object. Okay, now this object x is not coming from any set or anything like what we have in the axiom of specification, but in universal specification it's any object x. We have a property px pertaining to x, that is for a given x, px is either true or false. Okay, so this is the condition. Then there exists a set specified like this, such that for any object y belongs to this set px is true if and only if py is true. Okay, so this is almost like the axiom of specification. The only difference is that the objects are not coming from some set. That's the difference. This axiom, so in the beginning of this axiom, we are just given a property. We are not given a set and a property that the objects of the set may or may not satisfy. That's not the case here. We are just given a property. That property itself is defining a set. Now, this axiom is also known as the axiom of comprehension. It asserts that every property corresponds to a set. Like we have this property px, it will define a set. It is the set of those objects, whatever the objects may be, that satisfy this property. If we assume this axiom to be true, keep in mind that the motivation for creating this axiom is this observation that many of our previous axioms have a similar flavor, that they are like this. So with that in mind, we have created this axiom. Now we want to see where this takes us. So this axiom to be true, then we can, for instance, talk about many things, since the objects are now not coming from any set, but they are just objects in their own right. So we don't have any restriction of sets. We just consider some class of objects and call that class a set. Talk about the set of all, say, blue objects. The set of all natural numbers. The set of all sets. We can now consider that also. The set of all sets and so forth. Okay, these things can be considered now thanks to this axiom of universal specification. Also, this axiom implies most of the axioms in the previous section. So many axioms, almost all of them are consequences of this axiom. So it seems like instead of those axioms, we can just have this one. And this is the content of the first exercise of this section. Okay, so far things look good, but here is the problem. Unfortunately, this axiom cannot be introduced into set theory because it creates a logical contradiction known as Russell's paradox. Which was discovered by Bertrand Russell. He was a philosopher and logician. Bertrand Russell in, okay, let me just in 1901, and the actual paradox, we are now going to that. Okay. the paradox can be or is described below. Okay, so what goes wrong if we assume this axiom 3.8? So we start with a property. Since this axiom says that every property corresponds to a set, so we start with a particular property. Let Px be the property means statement, something which is either true or false, that depends on x, be the property that x is a set and x does not belong to x. X is a set and x is not an element of x. Okay, it sounds silly, but we will see now that this can happen if we assume this axiom. For instance, most of the sets that we have seen so far, they do not contain themselves as elements. That's what natural or normal sets do. However, there are some sets, provided we assume this axiom, that contain themselves as elements. So let's just see some examples. For instance, P of this is true because P of this means I can take any object x here. Now I have taken a set. If whatever I am taking is not a set, then P of x is false. However, if I have a set which contains itself, then also for that set, P of that set is false. Okay, because 2, 3, 4 is a set and clearly 2, 3, 4 is not an element in this set. On the other hand, if we consider the set S of all sets, the elements in S are sets and S contains all the sets possible, all the sets that can be considered, whose existence and the fact that that is a set comes from this axiom 3.8, whose existence follows from axiom 3.8. If S is the set of all sets, then S belongs to S. Do you see how strange this is? Because S is the set of all sets, it has to contain all sets by definition. But S itself is a set, so S must be in S as an element. So PS is false. Okay, but S is not our main concern. We are going to write down a new set using axiom 3.8. Now, axiom 3.8 implies that the following set exists. What set? Let me denote it by omega. It is the set that is determined by this property, this Px, such that Px is true. And if I write down what Px is, then it becomes this. X is a set and X does not belong to itself as an element. So far there is no problem. Axiom 3.8 ensures that this is a set. But now the problem will come. Axiom 3.8 specifically says that this collection is a set. Now, if we assume that omega belongs to omega, okay, suppose we are assuming that omega belongs to omega, because we have seen one example of such set. Who knows, maybe omega is an element of omega. Then what? If omega is an element of omega, then P of omega is true, because every element in omega is such that P of that element is true. Then I can write here, right? P omega is true. That is, but P omega is true means what? Omega is a set which is true. Omega is a set and omega does not belong to omega. So this looks strange because we have assumed that omega belongs to omega and the consequence is that omega does not belong to omega. Now what about the other, the other assumption? If we start with this, on the other hand, if we assume omega does not belong to omega, then since omega is a set, omega is a set and omega does not belong to omega, that means P of omega is true, then P omega is true and hence omega belongs to omega, okay, because it satisfies the condition for being in omega as an element. In bracket you can write by the definition of omega. So in any case we have both omega belonging to omega and omega not belonging to omega, which is absurd. This is the paradox, and you cannot find a mistake in this argument. The only thing where things are somewhat doubtful is the Axiom 3.8 itself, because all of this has come out as a consequence of that axiom. The problem with this axiom, with axiom 3.8 is that it allows us to create sets that are far too large. They are too large to be sets. Okay. For instance, it allows us to talk about the set of all objects. This is even worse than the set of all sets. Okay, according to this axiom, there is a set of all objects, that is the largest set possible according to this axiom. Set of all objects is so-called universal set. And clearly, just like this Russell's paradox, that set will also eventually create some sort of absurdities like this. This problem of having extremely large collections can be resolved by arranging objects in a hierarchy. And this is how we are proceeding in axiomatic set theory. We are starting from small sets and we are making larger and larger sets. We are not at once saying that, see, here there is a set of all objects. Not like that. We will go from the bottom towards the top. So that is known as hierarchy, and let us just see what it is. Let's elaborate on this. So the objects in set theory are to be arranged in hierarchy. At the bottom of the hierarchy are the primitive objects. That is, objects which are not sets, which are not themselves sets. We have already talked about this. However, since we are dealing with an impure set theory, for us there are primitive objects. For example, the natural numbers. However, in pure set theory, since they will also be constructed using sets, so there will be no primitive objects. So that's what is written here. In pure set theory, there are no primitive objects. Just a primitive set Primitive set means that can also be taken as a primitive object, but it's in the next rung of the hierarchy. Okay, so for instance, so these are at the very bottom of the hierarchy, there are just primitive objects. For instance, the natural numbers or the natural number. We can take one example, say 37. This is a primitive object. Okay. In the next rung, of the hierarchy, we have sets whose elements are only primitive objects. At the very bottom we have the primitive objects, then using them we create sets. Okay, so in the next rung we have sets of primitive objects whose elements are only primitive objects. For instance, the set, say 2, 3, 5, it's a set whose elements are primitive objects, or the empty set. Okay, for the sake of this, for the purpose of discussion, let's call these things primitive sets. That is, primitive sets are either the empty set or non-empty sets in which the objects are only primitive objects. Okay, let's call them primitive sets for now. Then in the next rung we have sets whose elements can be primitive sets and primitive objects and or primitive objects. Then we consider sets whose elements are only primitive objects and primitive sets. For instance, the set, give me a moment. For instance, this set 3, 4 and again a set. Okay, here 2 elements are primitive objects and 1 element is a primitive set. Then one can consider sets made out of these objects and so forth. So it's like this. We have the primitive objects here at the bottom. Then we have sets. In the next rung we have sets consisting of primitive objects. Then in the next higher rung we have sets consisting of primitive objects and primitive sets. Okay, and then it goes like that to more and more complicated sets. Okay, but what is the point in doing all these things? The point here is that at any stage of the hierarchy, since we will have sets whose